So I have a problem here. I have an angle that's sitting on an incline. Okay? I have the measured value here. I have the velocity value here. But that's all I have. Okay? And what I need to do is I need to figure out how long it will take for it to come to a stop at the end of that incline. So when it reaches the end of that incline, how much further will it travel before the penguin stops? Now I also know that the velocity is constant as it's sliding down that incline. Well, that's an important piece of information. First step for a problem, the diagram. And there's two actually to draw. There's one here and one here. Okay? So let's start with this one. These are old typical square penguins. They're pretty common in Antarctica. You just got to do a little look around on that one. What are the forces on that penguin? Well, there are three. The weight, the normal, and lastly, the force of friction. They do tell me that the coefficient of friction here and here are equal, so that leads me to believe that there is friction in this problem. Okay? Now looking at this part of the problem, my free body diagram would look like this. It's the exact same three forces, but the orientation has changed. The weight straight down. I have my normal, which is always perpendicular to my surface, and then the force of friction, which is always perpendicular to my normal. Okay? I'm going to constantly incline in this video, and the follow-up video we'll use this free body diagram to solve for the test. I think it was higher. I don't quite remember. Okay, so how do I do it? Is I need to change my coordinate system. Because if it was an unbalanced system, I would expect this penguin to accelerate down that incline. I'm going to try to take advantage of that motion by shifting my axes so that presumed acceleration, which doesn't exist in this case, is down one of my axes. It makes the math a lot easier if I do that. Okay? And then, in addition, I have already two vectors that are situated along an axis. They're always perpendicular to each other. So it only makes sense to make my math easier to shift my axes to take advantage of that configuration. Okay? And that's my x. Now, they're orthogonal to each other, so they're independent. So when I go back and I look at Newton's second law, sum of my forces is equal to mass times acceleration, I can say sum of my forces in the x, sum of my forces in the y, because of that orthogonality. Okay? So what forces do I? My x direction is in this direction. Okay? So right off the bat, I have a force of friction. I went ahead and said that this is my positive x. So the force of friction would be negative. But that's not the only force in the system. If I were to superimpose that coordinate system, you can see that a portion of my weight, let me use a different colored chalk. My portion of my weight is in this direction, and a portion of my weight is in this direction. Okay? So, there's a portion of my weight that's down the x-axis. Well, that turns out to be the exact same angle as that. That theta here is the exact same angle that. So that portion, this part right here, is equal to sine theta. So I end up with cool? Doing the exact same thing for my y-axis, I end up with normal minus mg cosine theta. Okay? Well, that leads me to normal equaling mg cosine theta. And the reason that's true is that this is equal to 0. And this is equal to 0. If that's equal to 0, I'm just going to move my mg cosine theta on the other side. Okay? Now, force of friction, not that way. Force of friction is equal to the coefficient times the normal plus mg sine theta. Okay? I can take this, plug it into there, and I'm left with mu k, oh, that's all equal to 0, mu k mg cosine theta plus, oh, not a plus, oh, this is negative. There we go. That makes sense. Okay. I'm going to move this over to the other side, but the first thing I'm going to do first is get rid of that. Move theta over to the other side, and I'm going to be left with negative mg, or negative mu k, my coefficient of friction, times cosine theta is equal to sine theta. Okay? No. Divide by negative cosine, I'm left with mu k is equal to sine theta, which is equal to the tangent of theta. Okay? So after doing all that work, the solution I end up with, the most important part, is mu k is equal to tan theta. Now, this is a shortcut. If the only force you have at if the only forces that are acting on my system are weight, friction, and normal, and the object is not accelerating, I can jump right away and say that the coefficient of friction is equal to the tangent of theta, the tangent of that angle created. Okay? With this bit of information, we're going to move on to the second part of that problem. Cool? And that's on the next video.